Intro to Calc. Hope you guys are having a fantastic day. We are moving, oops, I think that's supposed to be 221, 2.2.1, because it is Chapter 2, Section 2, Day 1. And this is the intro to the derivative, which is one of the main ideas, one of the main concepts of calculus. Today specifically we're going to be talking about the derivative at a specific point. So I'm just going to add that to the title here. So the next video we're going to talk about the derivative as a function, and so that'll be a little bit different than today, but they're super closely related. So today, hopefully by the end of this lesson, you should be able to understand what a secant and tangent line to a curve is, define a derivative graphically and algebraically, and be able to calculate the derivative using the limit definition. All of these are only at one specific point. We're not going to talk about the derivative for all points on a curve yet. That's going to be the next lesson. So the first two vocab things that you kind of need to know, because I will probably use them at some point in the future, is what a secant line and a tangent line are. So if you remember from before the previous videos, previous lessons, we talked about, say I have a curve, we talked about finding the average rate of change between 2 points. So let's say, for example, this is point 1 and this is point 2, and we're curious to know like the average rate of change, and that would be, you would find this line between the 2 points and you find the slope of that line. So this line that connects 2 points on a graph essentially is called the secant line, and the slope of this line gives you the average rate of change. It also gives you the approximate slope of the graph at that point. So that's kind of what a secant line is. Now, if I find the secant line between a point that is closer to the point I'm interested in, this line, or the slope of this line, gets closer and closer to the actual slope of the curve at that point. But you're still, every time, the slope of the line is the average rate of change until you get that point to be exactly here. In which case, then you're finding the average rate of change between a dot and itself. So theoretically, right, you're not actually going over anything. So you're actually dividing by 0, which is not possible, which is why we have limits. It's why we have derivatives, because a lot of times we're interested in the slope of the curve at a specific point. And the slope of the tangent line is that point, is that value. So if I'm like, here's my function, right? The slope, right, the closer and closer this point gets to the one I'm interested in, the closer and closer I get to get my secant line slope to be equal to my tangent line slope. So the tangent line is the line, that's like a really bad drawing, but the idea is it goes through exactly 1 point on the curve, because it lies tangent to the curve. So here's a nice little visual so you can see. So the secant line is the line connecting 2 dots on, or 2 points on a curve, and the tangent line just touches the point on the curve, and it is, the slope of the tangent line is equal to the slope of the curve at that point. So that's the difference between a secant line and a tangent line. Okay, so there's kind of the definition, the difference between secant and tangent line. So just as a recall, that the average rate of change of a function over an interval from like a to a plus h, or from like 3 to 3 plus h, or from, basically you have a point on x and you go over h and you have a new point on x and you want to know the average rate of change from point A to point B, you do the function, the y value at the second point minus the y value at the first point, divided by the x2 minus x1, which is just h. And so the instantaneous rate of change takes that value of h, right, and it brings it really, really, really small, like infinitely small. And so it's basically, right, the same thing as this, but the limit as h approaches 0, because what we're doing is we're kind of zoning in on that point. Okay, so there's your instantaneous rate of change. Now, this instantaneous rate of change, which is also the slope of a curve at a point, right, or also known as the slope of the tangent line, is the derivative. Like I said, big major concept in calculus is to understand what the derivative is. So this is our like day one of the derivative. Couple funky things. There's like a couple different notations of the derivative. I'm going to go over one of them today. And again, recall that this is just the derivative at a point, not the derivative function. Okay, so the derivative of f of x, so given that f of x is a function, the derivative of f of x at x equals a, which is written as f prime of a, so that's just like an apostrophe there, and this is the notation for a derivative, one of the notations for a derivative, and we say it as f prime of a. And so then the rate of change of f at a is f prime of a, which equals the limit as h goes to 0 of f of a plus h minus f of a over h, right, which is the same thing that we showed above. If the limit exists, then we say that the function is differentiable at a. So derivative, differentiable, is basically like, differentiable means like you can take the derivative at that point. And we'll talk about when you can't take the derivative at a point, but for right now we're going to look at only differentiable functions. Okay, so here is an example. So let f of x equals 3 to the x plus 1. I can write English. Estimate the derivative numerically and graphically. Okay, so in order to do this, we're going to want to start by graphing f of x, and then take a guess about what like a good estimate of the slope of the tangent line would be around x equals 0. Okay, so I'm going to start by graphing it on my calculator. So I go into y equals, I'm going to clear out whatever function I had in there before, and I have 3 to the x plus 1. Okay, and then I want to graph that. So, it looks like I have other stuff in there, so I need to clear that out. So second quit. Let's, annoying calculator, let's quit out of there. I apologize for wasting time right now. Okay, so I need to clear out, you might have something in here as well. So if you go second y equals, you want to clear out whatever your stat plots are. Or some other function, other things that you have going on. And we're curious to know what the slope of the line is at x equals 0. So maybe we want to like zoom in a little bit. So I can tell that this is at the point 0, 2. So I'm going to actually zoom in on that area. So I can do that a couple ways. I can change my window and say, I want to go from x from -1 to +1. And then my y, I want to go from like maybe 0 to 2.5, or maybe 1 to 3. Maybe 1 to 3. I think that would be better because that's kind of zooming in on that point that I'm curious about. And I'm going to graph it. And so I'm still, again, I want to know what the tangent line is at this point, at 0, at x equals 0, y equals 2. So just to make sure you're doing it right, you want to like take a guess. And if you can see on this graph, right, my slope of my tangent line is going this direction, which means it should have a positive slope. So like my answer should have a positive value, not negative, right? If it was going down, it would be a negative value. So that's kind of something to keep in mind, just to make sure that like my answer is generally correct-ish. So for my estimate of the slope of the tangent line, I actually found the average rate of change from -1 to 0. Maybe you did from 0 to 1, or -1 to +1. But basically, this should give me a general idea of where my answer should be. And so I did, f of 0 minus f of -1 divided by 0 minus -1. And so I end up getting 2/3 as my estimate for my slope of the tangent line. So B asks for a good estimate of the equation of the tangent line to f of x at x equals 0. So remember that for a line, you need a slope and a y-intercept, or if you want to use point slope form. But if you want to use, other way around. If you want to use slope-intercept form, right, you need, which is y equals mx plus b, you would need a slope and a y-intercept. And in this case, we do actually have the y-intercept. We know that from the graph, right, that it goes through the point 0, 2, or 0, 0, 2. If you don't know that, point slope form might be a little more useful. So, side note, point slope form versus slope intercept form, just as a refresher. All right, if you need them, quick refresher, two different ways to write equations of lines. You have point slope form, which is y minus y1 equals m times x minus x1, if x1 and y1 is a point on the line and m is the slope. And then slope intercept form is probably what you're more familiar with, where m is the slope of the line and b is the y-intercept. So in this case, since we have an approximate slope of the tangent line and the y-intercept, because we know that that line has to go through that point, 0, 2, then our approximate equation of the tangent line is y equals 2/3 x plus 2. And then you can also explore it using a table. So what I would do is probably put it in my calculator and look at the table on the calculator. So same way, you can, here are my table values for 3 to the x plus 1. And so you can do 2 points that are really, like a point that's really close to 0, 1, or 0, 2, sorry, and find the average rate of change, and also get another estimate for the derivative at that point. The second example is an algebraic, computing the computing the derivative algebraically. So go ahead and try it, see if you can figure it out, then I'll go over it real quick. Okay, so to start for this one, right, remember that our function was x plus 1 squared. So I start out with the limit definition, right, that the limit as h goes to 0 of f of a plus h minus f of a over h. In this case, right, we're curious about the function at x equals 0. So that's what a is, right? A is the value that you're looking at on the x-axis. So I replaced all my a's with zeros. So basically what I have is f of h minus f of 0 divided by h. And in this case, when I plug in h for x, I get h plus 1 squared, and then I get 0 plus 1 squared divided by h. This is, again, just plugging these values in for x. And I end up with the limit as h goes to 0 of h plus 1 squared minus 1 squared over h. Foil that out, and you end up with h squared plus 2h over h. Your h's cancel, and you're left with the limit as h goes to 0 of h plus 2. Remember, you can just plug in 0 at that point because you're not dividing by 0 anymore, and you get the limit equals 2. So the derivative at x equals 0 of x plus 1 squared. The equation of the tangent line, we know it goes through the point 0, 1, so your line is y equals 2x plus 1. 3 is more challenging, significantly more challenging. If you're up for it, try it. And here's the answer if you wanted to take a look at it.